1. This is version 2. I'm going to write that up here. Number 1. Which of the following molecules contains central atom with sp2 hybridization? I'm going to have to decrease that to get them all on the board. There we go. Remember when we did, let's see, the number of groups surrounding the central atom, groups of either bonds or lone pairs. If you can have 2, 3, 4. I didn't put 1 up there because that doesn't make any sense. And 5 and 6. And then the electronic geometry would be for 2, you'd have linear. 3, you'd have trigonal planar. 4, you have tetrahedral. This is just a review. This one is trigonal bipyramid. And this one is octahedral. Let's see, I'm going to make some room over here. Now, as far as the hybridization goes, to accomplish these geometries, and you do the hybridization first before you look at the molecular geometry. So the hybridization for linear is simply sp. Right, trigonal planar is sp2, tetrahedral is sp3, and trigonal bipyramid is d sp3, and octahedral is d2 sp3. It's really very simple. With 2 groups, you need an s and a p. You know, two orbitals combined to make 2 hybrid orbitals. And trigonal planar is 3, 1, 3, 4, 5, and 6. So it's really simple. Okay, now to answer the question. So we have let me do it this way, B, C, D, and E. So A, we have aluminum, and we have hydrogens on this side like that, like that, like that. Then we have phosphorus and 3 chlorines, right, with their lone pairs. Right, every chlorine has an octet. Everybody's got an octet. Hydrogen has a duet. Okay, sp2 hybridization says 3 groups around the central atom. Right? Central atom would be this one or that one. They got 4 groups around each one. That's sp3. So that's not the right one. Okay. Boron trifluoride. Like that, like that, like that. Let's see. Boron has no lone pairs around it. Fluorides all have octets. Right? 1, 2, 3. That's sp2. Okay. And we could look at the others, like phosphorus and then hydrogens, but a lone pair around that one. So that's 4, that's sp3. And then the nitrogens with, what are these? Hydrogens. I think that's hydrazine. But these have lone pairs here also. So each of those nitrogens has an octet. It's got 4 groups around it, which means they're sp3s also. And then beryllium with chlorine here and chlorine here, that would have to be sp. Because there are two groups around the beryllium means sp hybrid. Okay, so the only one that fits is this one for sp2. All right, number 3. I'll leave that chart up there because we might use it again. It's more work to use a microfiber cloth, but it cleans better. Number 3. Consider the molecule and the following hybridization choices. What's the hybridization of the carbon atom that is double bonded to oxygen? So we got 4 carbons. Okay. We got an oxygen here. That's called a carbonyl group. If you end up in organic chemistry, you'll see that again. Chlorine, hydrogen, and triple bonded nitrogen. Okay. In order to determine hybridization, remember, we got to have all the electrons counted for. All right, there's 4, there's 4, there's 4, and there's 4. The only one's missing that lone pair right there. But we're only interested in the double bonded to oxygen, this one. What's the hybridization for this one? 1, 2, 3 groups is trigonal planar, or sp2. So that's why the answer is B. Let's see. There's another one. Hybridization of the nitrogen. How about the nitrogen? It's not highlighted, but since we've already got it on the board, well, nitrogen has 1, 2 around it. So it's sp. This is sp2. And this one's sp also. The rest of them are sp3. Well, we left out. Let's see. There we go. Now they're complete. And this one's sp3 also. So that's tetrahedral, trigonal planar, tetrahedral, linear, and linear. In case I get sneaky. Oh, that's number 5. Right, that's number 5. 3, 2, 3, and 1, 1. Oh no, it's a different molecule. I'm sorry. No, my mistake. Let's put it up here. It's a different molecule. 1, 2, 3, 4, 5 carbons. Okay. I saw that nitrile group on the end and got confused. This one has 2 hydrogens. They would be like this. Remember when we write this shorthand version in organic chemistry, the carbons are always bound to each other, and any hydrogens are bound to the carbon they're closest to. So the carbon on the left has 2 hydrogens. Yeah, 2 hydrogens here. And then we had a double bond there. And that hydrogen that's attached to this one is here, like that. And then this one has a carbonyl. And this one has 2. And that was, okay, so we just need the lone pairs here. Now that's complete. So now we can assign the hybridization. Right? 1, 2, 3, sp2. 1, 2, 3, sp2. 1, 2, 3, sp2. sp3. 1, 2, 3, 4. 1, 2, sp. And just for the carbons. Yeah, just for the carbons. So it's 2, 2, 2, 3, and 1. 2, 2, 2, 3, and 1. A would work. Okay. Am I going too fast?
No, you're good.
Oh, okay. All right, now we're headed for 6. Hybridization of selenium and selenium hexafluoride. So if we start from scratch, selenium is in the chalcogens. That means it has 6 valence electrons. And halogens have 7 times 6. Right? So that's 42, 48, right? 48 electrons. Okay, so we know that selenium's in the middle. 1, 2, 3, 4, 5, 6. Two, 4, 6, 8, 10, 12 equals 36. Okay, 2, 4, 6. If we put 6 more to make an octet around each fluorine, 6 times 6 is 36. Use them all up. Okay. Just to be complete. There we go. So what was the question? Hybridization of selenium. That's 6 groups. It's D2sp3 octahedral. Okay, that's E. Now, is that kosher? Yeah. Selenium's in the 4th period. That means it has access to 4D orbitals for hybridization purposes. Right. Let's stop at 8 for a second. Because I don't know why I didn't mark this one, but that's the skeleton. We have 1, 2, 3, 4, 5, 6 carbons. There, carbon, 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 and then a nitrogen, 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 nitrogen. Okay, if that's the tetracyanoethylene has this skeleton, and we have to assume there are no hydrogens in there. We weren't given any hydrogens. So that means 1, 2, 3, 4, 5, 6. 6 times 4, 4 valence for carbon is 24. And then 1, 2, 3, 4 times 5 is 20. So we have 44 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used up 18. So we have 26 electrons left. Where are we going to put them? Well, we start from the outside, work our way in. 2, 4, 6. 2, 4, 6. 2, 4, 6, and 2, 4, 6. That's 4 times 6 is 24. So that's 2 electrons. Where do those 2 electrons go? Normally, what we would do is work our way in and put them around one of these carbons. But if we do that, then there's no way to make an octet out of these because it's up here. Right? It could make a double bond here or it could make a double bond there, but it couldn't make one here unless we allow for translocation. So we're going to put those 2 unused right there. Now we would make an octet around this carbon. We could use 2 of those, 2 of those, 2 of those, and 2 of these. And then we can make an octet here like that. And that would get everybody an octet. And then the question was, how many of the atoms are sp hybridized? Sp is linear. So there's 2, there's 2, there's 2, there's 2, there's 2. So we've got 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 linear. How many of the atoms are sp hybridized? Why does it say A? That's an error. Yeah, that's an error. I think it meant to say how many are sp2 hybridized. Did I make that correction in your copy? Because this is an old key. It should be eight.
See,
8 are SP hybridized. And there are 2 that are SP2 hybridized, these 2. See, this one is 1, 2. This one is 1, 2. Right? So you got 1, 2, 3, 4, 5, 6, 7, 8 SP hybridized. That's an error. That one should be D. I'm going to change it up here. D. Here we go. Rather than try to change it to SP2. And then let me take a look at version 2. Yeah, there's version 2. Oh, number 8. Number 8. Yeah, okay. My version 2 key is correct. Well, let me go over here to number 8. Somebody's zooming in. Yeah, okay. So there's no error in your documents, I don't think. But there is an error in this key. All right, we just fixed it. Oh, there's Jade. Let me zoom. Missing Adam. No, John. Adam's the last name. Okay, and that one wasn't highlighted, but I thought it was worth taking a look at. Okay, now the next highlighted one, number 9. Okay, a pi bond is the result of, remember how we get a pi bond? First of all, if you've got 2 atoms bonded together, you start with a sigma. Right? There's your sigma. It's on axis between the atoms. Any pi bonds are off axis. Say we have 1 pi bond here. You have to have a sigma before you can have a pi. Now you can have 2 pi's, but in this case we have 1. How did we form that 1? We formed that 1 by the overlap of unused p orbitals. Right? At least with the localized electron model. That's how it works. So D, sidewise overlap of 2 parallel p orbitals. That explains the pi bond in the localized electron model. Or the valence bond theory, and the model comes under that. How about 10? Use these molecules to answer the next questions. Which molecules have p orbitals that share an electron pair to create pi bonds? Well, look what you got. You got these, this one. See, I'm putting them in the same place they do. There, there, and there. And then you got this one with there, there, and you got this one. Like that. So how many of them have pi bonds? All of them. All 3 of them. This one has 1 pi, this one has 2 pi's, and this one has 3 pi's. So all of the above. All of them meet the conditions. P orbitals overlap. Now for these guys, this is a single pi bond. These are conjugated. Whenever you have a double, single, double, at least that group, then you have a conjugated system. So it's conjugated for this amount. But when you have 3 of them like this in a cycle, double, single, double, single, double, single, double, single, double, they all form a conjugated system, a special conjugated system in this case called aromatic. And these are extremely stable molecules. You are delocalizing the electron density over that entire molecule. Whereas here, you're only doing it over these atoms. And aromatics are very stable. Okay, number 11. Oh, based on the same models. Which molecules have equivalent carbon-carbon bonds throughout the molecule? All right. These bonds would be equivalent. When you conjugate systems like that, those bond lengths and strengths become equivalent because we delocalize the electron density over those. But these would be different. All right, so they're not all the same. This one is different from any of these others. Right? So this one, aromatics, all 6 of those bonds are exactly the same strength, exactly the same length. So A, right, the number 1, Roman numeral 1, that's the only one that has identical carbon-carbon bonds throughout the molecule. All right, go to number 12. The electron configuration of a particular diatomic species is this. What's the bond order for this species? All right. Let's see. We have that kind of complicated there with parentheses. This is 2s. Okay. So we're skipping the 1s, right? We're only using the valence molecular orbitals. But calculating the bond order works great for this. You don't have to use all of them to get that. Let's see, sigma star 2s. Then we go to, this is no mixing in this one. 2p and pi, 2p, and then sigma star. Oops, sorry, my mistake. Pi star. Did it go that high? Yeah, that's where it stopped, right? That's where it stopped. This one has 2, 2, 2. Pi's can have 4. Oops, but that one only has 2 in it, right? Yeah, this one only has 2. So where would they go? This shorthand method, remember this only has 1, 1, 1, 2 here, and 2 here. So these are paired. These are paired for that one. And these obey Hund's rule, and they are unpaired because there are only 2 of them in that degenerate orbitals. Okay, the bond order. We take the bonding electrons, 2, 4, 8, and subtract the anti-bondings. 2 and 2 is 4, divided by 2. So that's equal to 2. Right? D would be the answer. Now this is like if you take this and turn it like that, and then draw energy here, and put we assume it's binary. You have 2 atoms here, and then the molecule in the middle. This would be the middle stuff. Right? The shorthand method well, it's like doing electronic configurations. Only now we're doing it with molecular orbitals. 13. Right. As the bond order of a bond increases, the bond energy blank and the bond length blank. Okay, as the bond order increases. So if we increase bond order, what we're saying is we're essentially going from single, double, triple, right? Only fractionally. So as that increases, what happens to the first is the bond energy. Bond energy. As the bond order goes up, the bond energy goes up. It takes more energy to break that bond. And the bond length As you increase the bond energy, the bond length shrinks because with the strength of that bond, you're drawing those atoms closer together. So the bond length goes down. So it should be increases, decreases. C. All right, that was 13. 15. How many unpaired electrons in the F2 2+ ion are based on the molecular orbital theory? Okay, and the problem gives you the molecular orbital structure. I probably should have left that thing up there. I think draw it again. 2s star 2s. Yep. Sigma 2p pi 2p pi star 2p and sigma star 2p. I think we're going to need all of them. Yeah. Okay, so F2 2+ ion. F2 2+. If we have the neutral F2 molecule, what would we have? We're only working with valence here, so we're going to use the valence numbers. That means 7 for each fluorine. 2 times 7 is 14, minus 2 because we have a 2+ charge. So we have 12 electrons we have to position. Okay, 2, 4, 6, 10, and 2 more, right? So we don't need that last one. How many unpaired electrons? All right, these are going to be paired. This one is also, we got 4 in there. But this one is 1, 2. So we have 2 unpaired electrons in that structure. So is this diamagnetic or paramagnetic? Remember the difference? Para means alongside or with. So para is the one that is attracted into the magnetic field. That's what this is. Unpaired electrons makes paramagnetic. If they're all paired, that's diamagnetic, like diametrically opposed, right? It is rejected by the magnetic field. So our example is oxygen. Liquid oxygen poured into that horseshoe magnet will sit there in the magnet till it evaporates. Liquid nitrogen, you go right on through and stop. All right, 19. Let's see. Yep, okay. I need to get a drink here. See. Hybridization of the central atom of ClF2+. Now remember when you're trying to figure out which one is the central atom, the rule of thumb is you look at what you have to work with, and the central one is the one that's further to the left or below. It's more metallic than the other, and that's chlorine. Chlorine is below fluorine, so it goes in the middle. So then we can put the fluorines here, 2 of them. Let's add up, let's see, 1, 2, 3 times 7 is 21 electrons, right? 21 minus 1 for the plus charge. So we actually have 20 electrons. Okay, 2, 4, that's 16. 2, 4, 6, 8, 10, 12. 4. So we put the 4 lone pairs here. And to be complete, we have to put the charge here also. Otherwise, the number of electrons don't add up. We have to have that charge. Okay, what was the question? Hybridization. We have 1, 2, 3, 4 groups around the chlorine. That's sp3. 21. Which of the following does not contain at least one pi bond? All right, A, B, C, and D. Okay, what do we have to work with? H2CO. That's formaldehyde. CO2, C2H4, is it? Yeah, and C2H6. So there's one of them, it says, or none of the above. So at least one pi bond. All right. So this is 2 electrons, 4 and 6, right? Yep. So that's 12 electrons. I'm going to add up the electrons first. So this is 2 times 6 is 12 and 4 is 16. And this is 2 times 4 is 8 and 4 is 12 electrons. And this is 8 again, plus 6 is 14 electrons. Okay, now we can do the structures. Carbon's in the center, oxygen, and then hydrogens. 2, 4, 6. So that means 6 electrons left over. 2, 4, 6. Right. Now, we got to make an octet around that carbon. So we're going to take that. That's a pi bond. Right. So that's got at least one pi bond. And we're looking for the ones that do not contain at least one, right? So that one doesn't work. We've done CO2 before. Right. So that's got 2 pi bonds. Okay. C2H4 with 12 electrons. So we have 2 carbons and then 4 hydrogens. 2, 4, 6, 8, 10. That means 2 electrons left over. And then we're going to make an octet. That's another pi bond. C2H6. Hydrogens. 2, 4, 6, 2, 4, 6, 8, 10, 12, 14. Used them all up. No pi bonds in that one. So D is your answer. '24. Okay, 24. Complete the Lewis structure for the following molecule. This molecule has so many sigmas and so many pi's. Okay, so we got, let's see. We got 1, 2, 3, 4 carbons. 2, 3, 4 carbons and a nitrogen. And this one has an oxygen on the second carbon over and a methyl group. See, hydrogen, hydrogen, hydrogen. This one has a hydrogen here, right? Yep. And then 3 here. Okay, that's an octet, that's an octet, that's an octet. That's not an octet. So we would use that. And then that's an octet. And this, to make an octet, this nitrogen would have 3 of these around here. So we can do that and that, make a triple bond. And that gives everybody octets, except for the hydrogens. So this molecule has how many sigmas? Well, as many bonds as there are, that's the number of sigmas. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 sigmas, and then the double bonds will give you a pi each. There's a pi, and there's 2 pi's. So that's 3 pi, right? 13 and 3? Yep. E would be the answer for that one. Now, I went through that pretty quick because I know what to expect. But if you have any doubts, go back to your Lewis structure and just work it out. (26) Consider the skeletal structure below. Draw the Lewis structure. How many pi bonds does the molecule contain? All right. We also have to assume for this one that there are no hydrogens. We're only given 2 nitrogens and 2 carbons, or number 26. Let's see. Carbon, carbon, nitrogen, nitrogen. I'm going to do this full Lewis. So that's 2 times 5 is 10, and 2 times 4 is 8. 18 electrons. 2, 4, 6. It's 12. 2, 4, 6, 8, 10, 12. Now we can make octets. Right. We take these 2, that 2, 4, 6, 8. 2, 4, 6, 8. This one needs here also. There we go. So the question was, how many pi bonds are there? 1, 2, 3, 4. C is the answer. We didn't have to move electrons where we wouldn't normally expect them. Put them all around the nitrogen and then make our octet. That's the simplest way, and it works. That other molecule, there was no way we could get an octet on those central carbons by following that rule. We had to move the lone pair onto the central carbons in order to make an octet. 27. Which of the following contains the shortest carbon-carbon bond? All right. A, B, C, D. And E says B and D are the same. Okay. A is C2H2, C2H4, C2H6, and C2Cl4. So B and D are alike, but there's a significant difference there. The question is, which one has the shortest carbon-carbon bond? We did this one earlier, right? Like that, like that, like that. A single bond between the carbons. Okay? We did this one earlier. This one we've done before, but I'll do it from scratch in this case. 2 times 4 is 8. 2 is 10 electrons. So carbon, carbon, then a hydrogen, and a hydrogen, 2, 4, 6. That's 6 equals 4. So 2, 4. All right, how do we make an octet? Well, if we do this, that gives us 6 electrons. If we do this, that gives us 8. That's acetylene. Okay. If we're looking for the strongest bond, this one's going to be like that. So it'll look like this, only now you have 4 chlorines. But it's asking us for the shortest carbon-carbon bond. That would be the strongest bond. So the strongest bond between the carbons is that triple bond. That's the shortest bond. Okay. If we were to compare this one and this one, which one would be the next strongest bond? The next strongest bond would be this one. They both have double bonds, but chlorine has the nasty habit, since it's a halogen, it has a higher electronegativity than hydrogen. It has a nasty habit of drawing electron density away from the central carbons. And that weakens the bond and makes it longer. So that would be a weaker bond than this one. So if we put the bonds in order of strength, it would be strongest, next, next, last. I mean, that wasn't the question, but I throw it in for free. 28. Right. Okay, when comparing Be2 and H2, let's see, what are our choices? Be2 is more stable, H2 has a higher bond order, more stable, diamagnetic, paramagnetic. Okay. Okay, those are all molecular orbital questions or answers, 1 through 4. All right, so let's do the molecular orbitals for Be2 and H2. H2 is easy. We did that one in class. This is sigma 1s and sigma star 1s. These two electrons both go into that sigma. So the bond order for this one equals 2 minus 0 over 2 equals 1. How about beryllium? Beryllium 2. Okay. So beryllium has 1s and 2s. So beryllium is sigma 1s star, and sigma 2s star. So how many total electrons does beryllium have? Well, let's see, it has 4. We're using all of them in this case, not just valence. So it has 4 plus 4 is 8. 2, 4, 6, 8. So bond order here would equal to 4 minus 4 over 2 equals 0. Right? Yeah. We predicted that molecule doesn't even exist. What else? Let's see, stability. Okay, well, let's take them. Roman numeral 1, 2, 3, and 4. Okay, how about 1? Beryllium 2 is more stable because it contains both bonding and anti-bonding. And first of all, it's not more stable because the bond order is 0. That doesn't work at all. Roman numeral 2, H2 has a higher bond order than Be2. That's exactly right. 3, H2 is more stable because it only contains sigma 1s electrons. It's more stable, but that's not the reason. Or is it? H2 is more stable because it only contains, well, okay, you could look at it that way. It only has, this leads to a bond order of 1, and this and that leads to a bond order of 0. I guess, okay. I know they want us to pick 3. And then 4, H2 is more stable because it is diamagnetic, whereas Be2 is paramagnetic. Well, H2 is more stable, but it's not because they're diamagnetic or paramagnetic. That has nothing to do with it. And by the way, that's not right. They would both be, if this existed, they would both be diamagnetic because all their electrons are paired. So 4 is wrong on 2 accounts. All right, so we're going to say Roman numeral 2 and 3 both.
are good answers. That's kind of a weak question, I think, simply because of that number 3. 29. Okay, which of the following species is paramagnetic? All right, C2O2F2, C2O2, F2, and Li2. And then E is none. So that means what we mean by none is there are no paramagnetic. That all have to be diamagnetic. Well, we know oxygen is paramagnetic. We just have to prove it. So C2 is going to be sp mixing. Right? And in order to answer a paramagnetic diamagnetic question, we do have to have the proper molecular orbital sequence. So with, let's do electrons first. And we're only going to do valence electrons. So 2 carbons would be 8 electrons. Oxygen would be 12 electrons. This would be 14 electrons. And lithium would only be 2 valence electrons. Okay. So carbon, we're going to start with the 2s. And then we go to sigma and sigma star from the 2p's. 2, 4, 6, 8. That fills it up. So this would be 2, 2, 2, and 2, right? Is that right? No. sp mixing, right? So this is going to be, no. That's right. That's right. Right. Verify. Just go to the back of the document and look for C2. Okay, my mistake. I did make a mistake. Mixing. No, this is right here. 2 S's. Then we get, rather than sigma, we get pi from the 2p's, and then sigma from the 2p's. There we go. Then we get the stars, but I don't think we're going to need them. So 8 is 2, 2, and we can put 4 here. So we don't need this one. So this is going to be paired, 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 paired. This is diamagnetic. O2, 12. And O2 is going to be no sp mixing. So now we've got 2s, 2s. Then we go to sigma 2p, pi 2p, and pi star 2p, and sigma star 2p, if we need it. So that's 2, 4, 6, 10, and then 2. So we don't need this one. These are all full. This is the one that has unpaired electrons. This is paramagnetic. Okay. Then P2, F2. F2. And that's no mixing also. Two S, 2P, 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 and 2P. There we go. Okay, so 14. 2, 4, 6, and 4 is 10. and 4 more, right? 4 more. 8, 10, 14, that's right. These are both full. They're all paired, right? Because you have 2 orbitals each, and they're full. So this is diamagnetic. Lithium. Oh, which of the following is paramagnetic? Well, we found it, oxygen. Lithium only has 2 electrons, right? And lithium, we're working in the in here. Let's see, 2s, 2. That's it. So we found our paramagnetic right here. Should be B. Now, if you don't remember how to write those out, this molecular orbital page will be on the test. So it can back you up. 30. Let's see, what's 30 about? How many of the following does the bond order decrease if you add 1 electron to the neutral molecule? All right, there's C2. C2's there. O2's not. O2's not there. C2 is B in this one, isn't it? So who's C? Well, actually, it's not like that. A, B, C, and D are numbers. The first one is B2. Second one is C2. Third one is P2. And the fourth one is F2. So there we go. We got F2 already done. We got C2 already done. We need B2. So boron would have 6 valence electrons. And P2, now we're moving down. P2 is in the 3rd period, so we're working with 3 S's and 3 P's. And I assume that phosphorus is going to be like nitrogen. It's going to be sp mixing. So this needs to be reversed. And the subscripts also. This should be 3s, 3s. Let's see, P2 is 10 electrons. And then with sp mixing, the next one's going to be pi, 3p, and sigma, 3p. That may be all we need, actually. 10, 2, 4, 8, 10. Yeah, that's it. So those are all paired. Those are paired. Boron. Boron would be, let's see, 2s and sigma star, 2s, 2s. And then pi, because there's mixing, 2p. So 6, 2, 4, 5, 6. These are unpaired. See, those are paired. These are all paired. And those are all paired. So what's the question? For how many of the following does the bond order decrease if you add 1 electron to the neutral molecule? Bond order decrease. Okay, we need to do the bond order for each one. So the bond order here is 2 plus 2 is 4 minus 2. 4 minus 2 over 2 equals 1. And this one is 2, 4, 6 minus 2. 6 minus 2 over 2 equals 1.5, right? Phosphorus would be 2
4, 8. 8 minus 2 over 2 equals 3. Yeah, that makes sense. And for this one, that should be 1. But it's 2, 4, 8. 8 minus 6 divided by 2. So that's 1. Okay. So the question is, if you add 1 electron, bond order decrease. If you're adding an electron and you want to decrease the bond order, you add an electron to an anti-bonding orbital. If you add to an anti-bonding orbital, that will reduce this numerator and reduce this calculation. So we can look at these. If we add 1 here, it's to a bonding order. All right, so that increases by half. And that would be like that, right? Add 1 electron. Add 1 electron to this one, where does it go? Well, we have to move out here. Sigma 2p, right? Add 1 to that one, that goes up. Right. We added it to a bonding order. So that makes it, let's see, this is 5. And this one makes 7. So that's, wait a minute, is that right? 2, 6, 7. Yeah, 7 minus 2 is 2, 3, 4, 5. 5 divided by 2. No. Yeah, 5 divided by 2. 2.5. What was it to begin with? It was 6 minus 2 is 3, 1.5. That should only be 2 then. 6, 7 minus 2 is 5. Well, that messes me up. Well, now this one is 7 electrons, right? 3, 4, 5, 6, 7. Did I do it right the first time? With 8 electrons. 2, 4, 8. Yeah. 6 minus 2 is 3. Divided by 2 is 1.5. Now it's 5, 6, 7 minus 2 is 5.5. 2 times 2 is 4. You know, that messes things up. Now it's 9. Because I would have thought it would have gone up only a half, but it went up a whole. Well, numbers don't lie. That's what we got. If I'm looking at the right one. 2, 4, 5, 6, 7. That's 2. Yeah, that's right. Okay, made a liar out of me. That's not the right one, though. If we add another one to this one, where does it go? Well, now we go to I star. And that would make it 11. And that would make it here. That makes it 2.5. So that one went down. Right? Oh, how many? Okay, so that one went down. These two went up, up, and up. How about this one? Let's see. I star, oh, sigma star. That's the next one up. Yeah, okay. So now this is going to be 15, only it's here. 7, 1, and 6 is 7. Yeah. Okay, so that makes it a half. Right. Those two.
So two of them went down by adding an electron. That took a long time. Right. Oh, I didn't even put a number on that one. What was the number? 30. There you go. $32. How we doing on? Okay, we've been at it for an hour and a half. Order the following from shortest to longest bond. Don't forget the effect of atomic radius, orbital size. Okay. So if we're going to put these from shortest to longest bond, C2, B2, H2, and N2. C2, B2, H2, and N2. All right, so let's look at bond order. So carbon, yeah, is going to be sigma, sigma star, pi. Sigma, sigma star, pi. This is 2s, 2s, and 2p. Oops, 2p. All right, so we have carbon, hey, not in. Valence electrons, carbon's 4, 8. 2, 4, and 4 is 8. So the bond order here is going to be 6 minus 2 is 4 divided by 2 is 2. Talking about a double bond. Boron is going to be sigma, sigma star, 2s, 2s. Boron has how many? 6 electrons. This is 8 electrons, 6 electrons, 2, 4. Oh, we've got to go to pi. Pi 2p. Yeah, there's mixing, so the pi comes first. 2, 4, 6. So 4 minus 2 is 2. That's a single bond. This is a single bond. But it's made from 1s. We don't even need that one, right? 1s, 2 there. And then nitrogen, we know it's a triple bond. Bond order should be 3, and it's let's see, 5, 10 electrons. And this is sigma 2s, sigma star 2s, mixing. Okay, so the next one is pi, and then sigma 2p, 2p. It's 10, 2, 4, 4, and then 2, right? 2, 4, 6, 10. Okay. So that would be a bond order of 3. Okay. The shortest to longest. So the strongest, our tendency would be to do 3 shortest to longest. Would be this bond length, shortest to longest. Now this isn't right, but this is what I'm doing first. And then these two, we have to decide which one of these. Right? These are 1s orbitals, these are 2s orbitals. So these nuclei can get closer together. So we would put it like this and then like that. Okay, here's the rub. If we're doing shortest to longest, overlapping 1s orbitals and bringing those closer together would actually put hydrogen down here. hydrogen is actually the shortest bond length. Even though it's only a single bond, those nuclei are very close together because we're overlapping 1s's, sigma 1s's rather than 2's. Right, and then the boron will come here. I think that's hydrogen, nitrogen, carbon, boron. Okay? That's why I put that hint in there. Atomic radius and orbital size. Okay, 32. Did you see my message?
I did.
Okay, good. Oh, you turned it in already?
No, not yet.
Oh, okay.
Too behind to be able to have it done right now.
Yeah.
But it'll get done.
Okay.
It'll be-
All right. And there are no more labs, so we don't have to worry about those. Just the ones that are missing. So, wait a minute. Which of the following has a bond order of 1.5? All right. A through D. All right, we have O2 plus. Let's see, N2 and O2 minus and C2. All right, I know the bond order here of 1.5. Bond order here is 3. I mean, it's a triple bond, so we don't have to worry about that one. And let's go ahead and do carbon-carbon. So that's, let's see, mixing, it has eight electrons. So we have sigma, sigma star from the S's, and then the P's start off with pi. So that's 8. That'll be enough. 2, 4, 8. So the bond order here is 6 minus 2 is 3, 1.5, right? Yep. That's not right. No, that's not right. 6 minus 2 is 4 divided by 2. That's a bond order of 2. Okay, how about oxygen? Let's see. No mixing. So we have sigma, 2s, sigma star, 2s, and then sigma, 2p, and pi, 2p. We'll add more if we need them. So this has 2 times 6 is 12 minus 1 for that positive, which is 11. 11 electrons. So 2, 4, 6, and then 5. So we have 4 here, and then we have a pi star, 2p, with 1. So we have 2, 4, 8. 8 minus 3 divided by 2. So that's 5. That's 2.5. This one adds another electron, right? So it would add another electron here. Oops. Brain's not working. Actually, it would add, this is without 1 electron. We added 2 electrons to get from here to here, right? So that would add 3 here, correct? So that would be 4, 5, 6, 7, 8 minus 2, 5 over 2. So that's 3. That's 1.5. Oops, that goes down here. All right. All right, so there's your answer. That one's 1.5. C. Okay. 34. All right, 36. Up to this point, we've been working with diatomic homonuclears. Now we've got a heteronuclear, Bn. Which of the following statements about the molecule Bn is false? Assume sp mixing. Which makes sense. Both boron and nitrogen are left of oxygen. And that gives them the opportunity to mix. So Bn with sp mixing. Okay, they're both in the second period. So we're going to overlap and get sigma, sigma star with the 2s, and then pi, and then sigma with a 2p, 2p. And let's see, boron gives us, we're talking about valence electrons here because I left out the 1s. So we got 3 plus 5, 8 electrons. 2, 4, and 4. Okay. So that's all we need. Now what's the question? Which of the following statements about this molecule is false? Okay. It is paramagnetic. That's false, right? Because these are all paired. It's diamagnetic. Oh, we found the false one. Bond order of 2. 6 minus 2 is 4 divided by 2. Yeah, that one's true. Total number of electrons is 12. All right, total number of electrons. We had 8 here, but we've got 2 s's and 2 s's, so that's 4 equals 12 total electrons. Right, so that C is true. 2 pi bonds. Well, what's the bond order? Two pi bonds. Okay. That's a pi bond. And there's one of them, and there's the other one, because it takes 2 electrons for a bond. So we have a pi bond here and a pi bond there. That's true, 2 pi bonds. And E can't be right, because we found the false one. A is false. It should be diamagnetic. All right. How about 38? Muscle spasm. 38. Which of the following molecules or ions is not paramagnetic in its ground state? A, B, C, D, and E. Okay. A is O2 and O2 plus, and then B2, and then NO with no mixing, and F2. F2 has no mixing, no mixing. B2 would be mixing, and O2 would be no mixing. Okay. Let's see. That's 6, 12 electrons. This is 11 electrons. You have to subtract 1. Boron is 6. These are valence electrons. 5 plus 6 is 11. And this is 14 valence electrons. Okay, so for the 2s, no mixing. So we do a sigma, 2p, a pi, 2p, and then a pi star, 2p. I think that's enough. 12, 2, 4, 6, and 4 is 10, and then 2 more. So that was paramagnetic. Is that the question? Which following is not paramagnetic? So that's paramagnetic. If we subtract one of these electrons, it's coming from here, right? So you only have 1 there. This is also paramagnetic because it has 1 unpaired electron. Boron is mixing. I'm pretty sure this is not going to matter. Yeah, it will. 2s sigma star, 2s, and then mixing puts pi first. So 2, 4, 6. That's paramagnetic. And if you need to check, just look at this sheet. It'll be included. NO. All right, NO, and we assume no mixing for this one. I think that's what it says, right? Yeah, no SP mixing. S to S. No mixing, we'll put this one first. And then this one. All right, 11, 2, 4, 6. And 4. And then pi star 2p 1. So that one is paramagnetic. All right, so F2 definitely has no mixing. 2s, 2s star, sigma, pi star, and sigma star, or 2p, 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 14. So we have 2, 4, 6, 10, and 4 more left. Goes right there. Those are all paired. So this one is diamagnetic. Difluorine is diamagnetic. All right. 40 is not highlighted. If 40 were highlighted, what would be its bond order? We did 40. It would be 4, 5, 6, 7, 8 minus 2, 3 equals 2.5. So 40 would be D. I don't know why I didn't highlight it. But we're going to 41. Ooh, okay, 41. Yeah, I remember this one from a previous class. We are not equipped to answer 41 using molecular orbitals because we haven't done any polyatomics, any 3s or bigger with molecular orbitals. And I did a little bit of research on it, not enough to actually do it, but this carbonate ion introduces another concept that we haven't considered. One, we know that we have bonding orbitals and anti-bonding orbitals. Anti-bonding. There's also non-bonding molecular orbitals. So we haven't touched that subject yet, so we're going to have to answer 41 from what we know in the valence bond theory. All right, which of the following statements about CO3 2- is false? CO3 2-. Let's do the structure first. All right. So we have 4 for this one. We have 6 times 3 plus 2 for those charges. So that's 18 and 4 and 2. 24. 24 electrons. Carbon, oxygen, oxygen, oxygen. That's 2, 4, 6 is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. And wait a minute. 2, 4, 6. 6 times 3 is, yeah, that's right, 18. There we go. We need to make a double, this is one where we would have to invoke resonance. But to answer the questions, we probably only need to do one side, like that. And then, of course, it has a 2- charge. Well, there's a Lewis dot structure for one of the resonance structures. We have 2 more where we put the double bond here or here. I don't think we need it to answer the question. Carbon is 1, 2, 3, sp2 hybridized. Okay. A is true. A, B, C, D. E says all the above are true. Oh. So A is true. We're looking for the false one, I think. Yeah. B, the ion is expected to be diamagnetic. All right. Based upon this model, we would expect it to be diamagnetic because there are no unpaired electrons in this model. That may or may not be true, but our expectations are that it's true. We would need the molecular orbital structure for this one to actually prove it. C, the CO bonds are different lengths. That's false. Even though we show them like this, where that one would be shorter than these two, we know that they resonate with 2 other structures, and that makes all these 3 bonds exactly the same length. So C is false. And then the ion has a total of 24 electrons. Yeah, there it is right there. Valence electrons. Right, is that what you were saying? Yeah.
Well, so it's not C, because it says C in your key, but you mentioned it as if you proved it.
Yeah.
Oh, yes,
C is
it's
true.
false. Okay, never
And
mind.
this, as stated, would be false.
Yes. Okay.
But I'd have to stick a word in there. 24 valence electrons. If valence, then it's true. Actually, the total would be, let's see, we left out period 1. So it'd be 6, 7, 8 plus 8 would be 32 electrons. It actually has 32 totals. Yeah, so that needs some work. How about 42? See what that says. Two. How many electrons are involved in pi bonding in the benzene? Benzene. Okay, C6H6. We drew a benzene before. It's a ring structure like that, like that, like that. And if we draw it with the valence bond theory in mind, then it would look like this. So how many electrons are involved in pi bonding? 2, 4, 6. 6 electrons. That would be D. Okay, 45. There. Which of the following has the highest bond dissociation energy? Bond dissociation energy is the same as bond strength, bond energy. How much energy is required to break the bond? So the one that has the highest would have the largest bond order, right? The strongest bond. A through E. A, B, C, D, and E. First one is the neutral dinitrogen. The next one is into minus then into 2 minus, then into plus, and into 2 plus. So let's start with this one. Dinitrogen has mixing. So we're going to start with the valence. Then we'll go to pi, 2p, sigma, 2p, and then we would go to pi star. And we'll see if sigma. We may need that, we may not. Okay, so that means we have 10 valence electrons here. 2, 4, 8, and 2. So the bond order, let's move this out of the way a minute. 45. So the bond orders here would be 4, 5, 6, 7, 8. 8 minus 2 over 2 is 3. Okay? If we add an electron, where is it going? That one's full, so it has to go in this non-bonding orbital. I mean, the anti-bonding orbital. Right? So we'd have 1 electron there. That means we would have 8, we'd have 11 electrons actually. And we have 8 minus 3 over 2, which would be 2.5, right? 5 divided by 2. Okay. This one we add 2. So it actually would be 8 minus 4 divided by 2, which would be 2. Then if we subtract electrons, in that case, let's see, we don't need this one. In that case, where are we subtracting the electrons from this one? We're subtracting them from a bonding orbital. So we'll come down here to sigma 2p. This would be down to 1. That would be 9 electrons. So we would have 7 minus 2, right? We have 1, 2, 3, 4. Let's see, 1, 2, 6, 7 minus 2 divided by 2. So that's another 5.5. And then this one does away with that one altogether, right? 2p. There are no electrons in that one. That's only 8. So it's 4, 5, 6 minus 2. 6 minus 2 over 2 is 2. Okay. So what was the question? The highest bond association energy is the neutral dinitrogen molecule. Yep. Stay put. Let's see, 47. Which of the following molecules or ions does not contain a central atom with D2sp3 hybridization? All right, let's see, we have 4 of them to deal with. A, B, C, D. All right, A is xenon pentafluoride ion. Plus, yep, plus. And then IF4 minus, IF4 minus, SF6, we did that one earlier. No, oh yeah, SEF5 minus. SEF5 minus, there we go. We're looking for, does not have D2sp3. D2sp3 is octahedral. Needs 6 groups around the central atom. So let's do electrons first. 8, this is 5 times 7. See, it's 8. Plus 5 times 7 is 35. Minus 1. All right, so that's 42, right? And then this one is 4 times 7 is 28. I see. Well, 5 times 7 is 35, plus 1 is 36. And this is sulfur would be 6. Should be 49, right? No. 6 times 7 is 42, plus 6 is 46. Oh, wait a minute. I think I did this one wrong. 5 times 4. 5 times 7 is 35. Oh, yeah, plus 1. I did that one right. Never mind. Selenium is 6 like oxygen. 5 times 6 is 30 plus 1. So that's 37. Okay. Now let's draw our structures. 1, 2, 3, 4, 5. 2, 4, 6, 8, 10 would be 32 electrons. This has a fluorine here, fluorine here, fluorine here, fluorine there, fluorine there. And if we put 6 around each one of these, that would be 5 times 6 is 30. With 2 electrons left over, they have to go right here. Okay, so that's 6 groups. This is D2sp3. All right, you have iodine with 4 fluorines. Actually, this, to be kosher, that should be a plus right there. So this is 2, 4, 6, 8 would be 28 left over. So 6 times 4 is 24, right? So that's 4, 2, 4, 2, 4, 6, 8. And this is minus. All right, that's D2sp3. That's 6 groups. We did this one earlier. D2sp3, definitely. Se and 5 fluorines. 2, 4, 6, 8, 10. That'd be 27 left over. If I counted that right. 6. Oh, I didn't count it right. Hold on a second. Five times 7 is 35. Plus 1. 42. There we go. 42, that'll work better. 2, 4, 6, 8, 10. 32 left over. So 5 times 6 is 30. And that's 2. So 1, 2, 3, 4, 5, 6. They're all D2sp3. All these contain central. Oh, that's why E is the answer. Things starting to get a little weak. All right. Let's see, those are just definitions. And let's see, come on, come on. I know there's another one in here. There it is. Okay. So we got a table and we need to fill in. 1, 2, 3, 4 across and 1, 2, 3, 4, 5 down. Let's see, we got 60. And we got electronic geometry, hybridization, and bond angle, and examples. Okay. And then across here, we have molecules A, B, and C. That Okay, the one we're given is A. SP3 hybridization. Okay. Then in the problem, it says molecule A has SP3, molecule B has two more effective pairs around the central atom. If B has two more effective pairs, where are they going to go? We used up the S and the P's. D to SP3. Okay. And then C consists of one sigma and two pi's. Remember, you can't have a pi unless you have a sigma. So if you got two pi's and only one sigma, it has to be a triple bond. There's no way around it. And triple bonds always mean sp hybridization. Okay, triple bonds mean linear, right, as does sp. This is octahedral. This is tetrahedral. Okay, bond angles for tetrahedral, assuming all positions are occupied, is 109.5 degrees. D2sp3, octahedral, got square, and then you got something in the middle here and like that. So every bond angle here is 90 degrees. And this bond angle, if these are occupied by atoms, would be 180. So the only two possibilities you have here, 90 degrees and 180 degrees. Maximum. And linear, of course, is 180 degrees. Examples. Well, methane's a good one. Or carbon tetrachloride, that's a good one. You could even get ammonia. Will be tetrahedral. Electronic. How about this one? Well, we just did one. It's SF6 be a good one. And linear. Well, let's see. Nitrogen. That's definitely linear. Another example, carbon monoxide. This would be like that. Okay. I think I got one more. Unless I missed my guess. Yeah. Let's see down here. Yeah. This is the last one. Okay. Draw the molecular orbital diagram for O2 and N2. That's why I give you such a big box. And actually, you could do it from memory if you knew the sequence of orbitals, or you can just go, yeah, go here, right here, right there, just duplicate it. But then in the bottom, explain why removal of one electron from oxygen strengthens the bond, and removal from one electron from dinitrogen weakens the bond. When you talk about bond order, the bond order for oxygen has anti-bonding electrons. If you remove one of those, that increases the calculation to a higher bond order because you're decreasing the subtracted part. Whereas if you remove one from nitrogen, you're removing a bonding electron, and that decreases the bond order. Actually, it makes them both equal. At that point, they're both 2.5. But that's the explanation for it. That's it.